Hello, students. We're going to be working with limits and graphs today. Our goals for today's session are that we can write limits using appropriate notation, that we can see limits on a graph and decide when a limit would or would not exist. And again, once we start to get into this, your copy will have this part filled in with some specific assignments from Khan Academy that go with this video. Just like in our previous video, this may have been yesterday, may not have been, but yesterday is my default language to talk about the previous video. What I'd like you to do is to spend a minute and to identify some characteristics about this graph that are different or similar from the one that we observed yesterday. I can't really tell, but I think there's also supposed to be a hole in this graph here, but it got eaten up by zooming in. I'm going to pause for a moment to have you figure that out. I'd like you to pause as well. Write down some observations and then continue. Some of the things that I notice about this graph are that it's a piecewise graph. It's got 1, 2, 3, arguably 3 or 4 parts, depending on how we're considering this point here. I don't know why that just ended up on erase. So we got a piecewise graph here. I've got another vertical asymptote. That reminds me of what we did yesterday. This time we have some numbers attached that appears to be at a x value of 2. We could say that as x approaches 2, I'm going to have to go with like from the right side to talk about this part of the graph. Y is approaching infinity. And as x approaches 2 from the left, that's going down. I'm going to say y approaches negative infinity. We also have this nice weird jump discontinuity here. I use the word discontinuity, so I'm going to say this graph is not continuous. We also have an idea of what it means to be continuous from Algebra 2 and pre-calculus. We're going to adapt that in calculus, but for now, graphs that are continuous are graphs that you can draw without taking your pen or pencil or stylus off your paper or screen. Graphs that are not continuous do not have this feature. As of a couple days for a couple videos from now, that will not be enough for us to say that. But that's a pretty good way for us to approach this from where you are mathematically. The other thing that's happening is we have this weird thing here where that point doesn't exist. So the point 0, 1 doesn't exist, but as x approaches 0, in this case from both sides, so I'm going to say from left and right, y appears to approach 1. We have a hole in the graph there. That's at the beginning of this page, but we're approaching it and not getting there. This also gets us 3 different types of discontinuities, just so we can have names for these. This is a point or removable discontinuity. This is a jump discontinuity. And this is called an infinite or essential discontinuity. Those happen when we have vertical asymptotes. Infinite, there we go, I can spell good. On the previous page, we talked a little bit about getting to some kind of notations for this. So for example, I said that as x approaches 2 from the right, y approaches infinity. One of the things that we get to do in math is we get to be lazy strategically and find some different ways to write things. This is going to be our discussion on limit notation, because I'm going to say what I said here, but in fewer words and symbols, so we can do this very quickly. And the way that we describe this would be is x approaches 2 from the right. We just put a little plus after that. So this is the limit as x approaches 2 from the right. I'm going to describe it. Oh, it's described as f of x. I'm glad I put that in earlier. Of f of x, and we're going to say is equal to infinity. This is somewhat problematic. We can't actually equal infinity. However, we can say that a limit is equal to infinity because a limit is about what are we getting close to. And as x gets close to 2 from the right, y gets close to infinity. We could say the same thing on the other side. As x gets real close to 2 from the left, y approaches negative infinity. The limit notation for this would be really similar to what we just had. The limit as x approaches 2 from the left of this function is equal to negative infinity. The other place we talked about getting really close to something but not actually getting there was with regards to that one other weird part of this graph. And when we have that, we're looking at this point here. We said that from both sides, so as x approaches, I like them right, the word approaches out this time, that's fun, 0, y approaches 1. It doesn't get there, but from both the left and the right, we end up at the same place, even if we don't actually reach that. The way that we write this in terms of limits is the limit as x approaches 0. We don't need a plus or a minus because we can say the same as for both sides of f of x, and that's going to be equal to 1. On the previous page, we talked about a couple of limits that do exist. Let's talk about times that a limit doesn't exist. And to do that, we're going to use the same point where the point doesn't exist. But we said that the limit as x approaches 0 of f of x is equal to 1. Because from both sides, my graph is approaching that same height. This might give you a clue as to places that limits might not exist. What I'd like you to do is to pause the video and think of some reasons that a limit might not exist. When it comes down to it, there are really 3 reasons why a limit might not exist. And really that comes down to just 2 reasons. The first place on this graph that a limit doesn't exist is at our jump discontinuity. And we can say that the limit from the left, the limit as x approaches 1 from the left of f of x is equal to 2. The limit as from the right side, so as x approaches 1 from the right of f of x is equal to 1. But if I asked you to actually tell me what the graph is approaching as we got close to 1, so the limit as x approaches 1, we can't say anything because we have to decide between these 2 values. And since there are 2 different answers that could be, this limit does not exist. Side note, there's a delightful scene in Mean Girls, if you have not seen that classic movie, where Lindsay Lohan shouts out the limit does not exist. This is what she's talking about. The other place that our limit does not exist is on this asymptote. And because we have a vertical asymptote where our limit is coming into 2 different versions of infinity, our limit also does not exist there. So our limit as x approaches 2 from the right is positive infinity. Our limit as x approaches 2 from the left is negative infinity. But because those are different numbers, we don't approach the same thing. The limit as f of x, where x approaches 2, does not exist. And it is okay to write DNE for does not exist in this course. And that's also okay on the AP test. The final case where a limit might not exist doesn't show up on this particular graph. In both of these cases where we had a jump discontinuity or what we call an essential or an infinite discontinuity, our limits don't exist at that point. What we call one-sided limits, just from the left, just from the right, are okay. But for a limit to exist, we need both sides to be the same. So we can say the limit as x approaches, I'm just going to genericize this and say x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x. This is the condition that will tell us the limit does exist at that point. I'd like you to also notice it doesn't matter that this point doesn't exist. That's a really important thing. And finally, I mentioned the case that does not show up here. Limits don't exist if things end up vibrating infinitely. So if we were to zoom real close to a point and we saw something on a graph that looked like this, if you kept zooming in farther and farther and farther, you might see that this just keeps vibrating closer and closer and closer together. If you want to see a great example of this, if you take a look at the graph of sine of 1 over x, as you get closer to 0, this graph is just going to keep making smaller and smaller waves. So it's never going to approach a single value. We generally don't see that in this course, but I wanted to mention that it does happen. For the next couple slides, what we're going to do is to find a whole bunch of limits. I'm going to ask you on each of these slides to pause, and I'm going to go through the answers. And I'll talk through a couple of them that I think are a little bit more confusing, but otherwise I'd like you to ask while you are in class in person to go over some things if you're confused about those. So please pause now. And here are those promised answers. For most of these, I hope they're pretty straightforward. We're looking at the limit from the left and from the right at x equals 3, which is going to be at this height. We're looking at the limit from the left and from the right of x equals 2 from the left, from the right. And this does not exist because we're approaching two different numbers here. At 4, even though this point doesn't exist, since we're coming to the same place, we're good. And that kind of gets at I as well. And then at 1, even though this point is identified up here, and I like that I just covered that up with blue stuff. So even though we have this point up here at the point 1, 2, the limit here is what our graph is approaching on both sides, which is 1. And then for m, how do f of 1 and the limit of f of x as x approaches 1 compare? Well, f of 1 is 2. That's where the point is. The limit is 1. Those are not the same thing. Those are not equal. Here's another chance for you to try these out. I'm going to do the same thing. I'm going to ask you to pause the video and then look at the answers. Please pause now. Please take a look at these answers. For the most part, these should feel pretty good for you. The two new ones that we added were as x approaches negative infinity. So if I follow this graph as it goes on forever, it looks like it's never going to change its height again. It's a horizontal line. That's why that's -2, and same for as x approaches infinity. That's why that's +2. The only other thing I wanted to chat briefly about was f of 2. We used the filled-in point instead of the open point there. If both of those were filled in, this would not be a function unless otherwise noted, and I can't think of any case that this is really true for this course. Everything that we care about here is going to be some kind of a function. It's funny in saying that, I thought of the times that we don't have functions, but those will be explicitly stated. And that's also a joke, but you don't get it now. And the last one of these, same thing, I'm going to ask you to pause, and then we're going to come back here afterwards. Please pause. Same deal, here are our lovely answers. We do have slightly more infinities than we usually do. We also have an annoying thing where at 0 we can't really tell where that is. So I said it's about 1.7. It's probably close to 1.8 because I totally counted those as 5 boxes instead of 4. I changed that to 1.8. And again, please feel free to ask if you have any questions about these. Otherwise, that's it for today.